Let's consider the following simple cases of effective stress. We are placing emphasis on the vertical effective stress, which we are going to call sigma z. And in all these cases, we have a water table, sometimes below the surface, sometimes at the surface. And sometimes above the surface, like for example during a flooding. And we have to wonder what is the vertical effective stress at the point shown in each case. And so if this is level ground, the solution is very simple, so let's do it together. We're going to look at the weight of everything above the point per unit area. And the weight of everything per unit area is stress. So the total stress is the weight of everything above, which is going to be equal to, if this is gamma saturated and this is gamma, let's call it dry, it may be moist. So this is going to be A gamma saturated plus B gamma dry. So this is a step number one, which is the weight of everything above the point. Then we need to get the fluid pressure, the pore pressure U, and the pore pressure U regardless of the system, whether it is hydrostatic, steady state seepage, caused by chemical reactions, it's always the same. Put a tube above the point and see how high the water rises in the tube. And the height of the water in the tube is the height in the piezometer times gamma water. That is the fluid pressure under any condition. And so in this case, it's a hydrostatic case. The water table is at this elevation, and so by equilibrium that gets established at the entry of the tube, the weight of the water above that point in the tube and outside the tube has to be the same. So the water in the tube rises a quantity A. So this is equal to A gamma water, the unit weight of water. And then step number 3 is this is in the z direction. The effective stress in the z direction is sigma z minus u, which is equal to A gamma sat minus A gamma water. We can factor out A is A gamma sat minus gamma water plus B gamma dry. Once again, this is true for level ground conditions. And then there could be one more step, but let's complete all these first cases. And so this is case C, and in case C, everything is saturated, so the total stress is going to be equal to the weight of everything above the point, which is equal to gamma sat times C. The fluid pressure, if we put in our mind a piezometer that goes all the way up, it goes all the way to C, so this is gamma water times C. And therefore, the effective stress in this case, let me make it small here, will be equal to C parenthesis gamma saturated minus gamma water. You can convince yourself that the effective stress, as the water goes up, the effective stress has decreased because the pore pressure has increased. And in fact, this is what is going to come out of these equations. Now, what happens in case C? So let's solve it again. And so when we solve it, the weight of everything above the point is going to be equal to C gamma saturated plus D gamma water. If we place a piezometer, an imaginary piezometer, by equilibrium, the water has to rise to the top. So the pore pressure is equal to C plus D gamma water. So let's put C gamma water plus D gamma water. And as you can see, when we subtract the sigma prime, Z is going to be equal to C gamma saturated minus gamma water, and this cancels out. Notice how interesting this is, because the effective stress in the intermediate case and the final case are exactly the same. That means that it doesn't matter how high the water is above the surface, the effective stress remains constant once the water has reached the surface, the Archimedes buoyancy of the system. So whether it is 1 centimeter above the sediment or 5 kilometers above the sediment in the near surface will have exactly the same effective stress, because the pore pressure due to the excess water above the seafloor cancels out. So to summarize, as the water table increases, the sediment is decreasing its effective stress. Once the water is above the surface during a flooding event or on the seafloor, then there is no more difference. The effective stress remains constant. Under level ground conditions, now we can also think of during burial, only during burial, without any unloading, we can also think that the horizontal effective stress is going to be equal to sigma horizontal effective is going to be equal to K naught sigma vertical effective. Now, this is true if and only if the following conditions apply, because by definition K naught is the ratio between sigma horizontal effective over sigma vertical effective under the horizontal strains equal to 0, and during first loading, during burial. And so we can use the same equation to compute the horizontal stresses in the 3 cases. Notice that once the flooding recedes, the water table comes down, it reaches the surface with no change in effective stress, but when the water table keeps going down, now the effective stress begins to increase, and there will be settlements if this is the first time that the soil is experiencing this drying condition. This will be exacerbated by capillary effects, but just by pure Terzaghi's effective stress, this will occur as well. Let's consider one more case. In this case there is a steady state seepage. And the reason for that is because there is Artesian pressure from underneath. So that means that if I had, under hydrostatic conditions, the pore pressure would have increased like that. This is hydrostatic. But if I go and I put a pore pressure filter or a piezometer there, now the pore pressure could have really shot up and it could have been much higher. So it's out of equilibrium. In fact, if I plot that pressure here, probably it would have been at this point. So it's not hydrostatic. That means that there is a gradient. We have to solve it right. We have to look at the whole energy, both elevation and pressure. But just for the sake of putting the pressure only, the pressure at the top will increase according to hydrostatic conditions, given the fact that it's a slow flow and that lake is holding that pressure at the top. But if you look internally, the pressure is going like that. And so this is when there is an Artesian and there is a steady state seepage. If you want to analyze this case, once again, the effective stress at the point is the weight of everything above the point, which is due to, let's say, A and B heights. And so the total stress is equal to A gamma water plus A gamma saturated plus B gamma water And then the pore pressure, you will have to solve for this triangle. So you have to start from this point, which is the hydrostatic case, plus the gradient of this line, which is starting from the Artesian pressure at the bottom, and do by a triangular balance, then you will know what is the pressure at this position. And so let's call this pressure at depth Z. So there is U at depth Z, at depth U at depth A plus B. And then the sigma effective stress will be equal to sigma Z minus U, as we have done it in previous cases. So recognize that in this situation, the pore pressure is going to be higher at the point. Therefore, the effective stresses are going to be lower because of this Artesian pressure. The situation could get even more complex or interesting if you do have the situation where you do have an Artesian pressure, so the pressure at the bottom really shoots up above the lake elevation or the river elevation, but while this is the point, there is a layer with very low permeability. There is an aquitard. So that means that there is no seepage across the system. It is hydrostatic on both cases, but from the top, the pressure is going to be increasing from this position down according to gamma water. This slope is gamma water. But from the bottom, is going to start from the Artesian pressure, which we said that is significantly higher, and go up with the slope gamma water. So this slope is also gamma water because is the effect that is pushing down is the weight of the water. So at the aquitard, there is actually a pressure difference. This is the pressure at the above the aquitard, and this is below the aquitard. Effectively, what this pressure below is doing is pushing the aquitard up. And therefore, all this weight is not acting down onto the point. So once again, the total effective stress, it will be the same as before. If this point is at the depth A, and the water level here is B, so this point will be equal to A gamma saturated plus B gamma water. Now, the pressure at the point is the pressure that you have to come and pick up from this diagram. So it will be the pressure at the bottom where the Artesian pressure is minus gamma water, the height with respect to the Artesian elevation. And so that will be the pressure that we're talking about, the pressure at point A. And so it's U at point A. And the subtraction is Terzaghi's effective stress, as always, sigma minus U. What is important to recognize is that in this case, whether it is steady state seepage, and we have an Artesian elevation is lowering the effective stress. In this case, it's hydrostatic because there is an aquitard, a thin layer of clay that is preventing the fluid flow. But if that is the case, it's picking up, pushing up the sediment above the point, and is lowering the effective stress at the point. The last example I would like to bring to your attention is the case where an anticline has formed and where lighter fluids may accumulate. This is critical for the formation of oil reservoirs and gas reservoirs, and also to have a reliable space to capture or to store, geologically store CO2 for the next few centuries. So this is the case. And somehow during the formation history, tectonics pushed this layer before the sediment actually accumulated, and it created this buckling, this bending of the structures, which are anticlines and synclines. So here we have an anticline where this is a fine-grained sediment. Let's say this has become a shale. And below that is the place where oils will form. So somewhere you have the source rock, where organic matter is getting processed, cooked at high pressure and temperature, like in a pressure cooker, and eventually oil droplets and gas droplets begin to migrate upwards, and they gradually accumulate beneath the anticline. Now, the fact that oil and gas migrated upwards means that they are lighter than water. Therefore, the pore fluid here is lighter than water. So let's take now an equivalent scenario, which sounds very trivial and probably not real, but it's actually exactly the same. Imagine that I have an upside-down bucket, and this is the water table. We're going to put it all the way to the top. This is the sediment, and oil and gas accumulated, and it has fully filled the reservoir. So that means that we have, up to this elevation, we have a lighter fluid, which we're going to call it gamma O for oil. And that could be CO2, or that could be methane, or hydrogen in the future. Well, this is water, and so I draw it like this because here we don't have a clear idea of what the boundaries are. So here the boundaries are clear. This is like a swimming pool. So if I place in an imaginary piezometer, the water will rise inside the piezometer to the water table. Now, this point and this point here must have the same pressure, otherwise the water would be migrating left and right, and so this is hydrostatic, everything is hydrostatic, so they have the same pressure. So at the bottom of the filled reservoir, the fluid pressure is exactly the same that outside. And so we can put some dimensions. Let's say that this is A and that this is B. And we can draw the fluid pressure in these systems. So outside of the reservoir, the fluid pressure increases with gamma water. So this is, this slope here is gamma water. Now, we reach this point where both points 1 and points 2 have exactly the same pressure, which is this one here, 1 equals to 2. Now I'm inside the reservoir, and as I go up in the reservoir, I'm going with a different gradient. I'm going with a unit weight of the oil unit weight. And so this is the pressure inside the reservoir. This is the pressure outside the reservoir. So notice that against the seal, I have this pressure from the top of the seal, and this is the pressure at the bottom of the seal. And this is the one that is going to drive flow through the seal, and the one that is going to create capillary resistance until the seal fails to properly store the fluids. So now you can see what is the pressure inside and the pressure outside, assuming that this is very, very thin. The pressure from outside, from out, coming from the top, will be A minus B gamma water. This is the height, A minus B gamma water. Now coming from the bottom, from U from bottom, is going to be gamma water times A. This is the pressure here, minus gamma oil times B. And the difference between the two is gamma water A will cancel out, and so the capillary pressure that the seal we have to resist is B, the column of oil, B gamma water minus gamma oil. If you compute this, even for a 100 meter oil column or gas, let's say oil column, this is going to be in the order of 2 kilonewtons per meter cube, so times 100. This is a fairly low capillary pressure that most seals will resist, except if during that process of folding, fractures develop, and those are the leak points. Finally, this buoyancy, because of this higher pore pressure from inside, is pushing this bucket up. Therefore, the effective stress in the sediment below the liner will be lower, similar to what we saw before with the aquitard. Now, what is the horizontal effective stress in this case? It's not so easy because, as you can see, the reservoir formed and then oil began accumulating. So this is a case of unloading, and the loading and unloading history do affect the horizontal stress. And so this is not a true K-naught case, and we will return to that when we look at state of stresses in soils. The last couple of examples bring other important cases that are of extreme relevance to the geotechnical field, from the near surface to petroleum geomechanics and deep boreholes. Imagine an excavation, and this could be just 10 meters or it could be 10 kilometers. And I'm going to zoom in on the face of the excavation. If it is unsupported, this will eventually cave in. So we want to push the walls of the excavation sideways. And so let's zoom in and let's see how do we do that. So this is the formation. So this is the wall and the formation. And inside, we are going to put a suspension, a fairly stable suspension, which is relatively heavy, made of mud, bentonite typically. Now, internally, this has a certain height, depth Z, so internally, the pressure is going to be Z times gamma mud. And the hope is that that fluid, that is actually the fluid pressure, that fluid pressure pushing the grains against the wall will stabilize the wall. How does that happen? Well, imagine a French press where we have a piston with a filter, and there is a suspension inside, and then we press on the French press. As we press down, if you look carefully, a cake begins to form of the grains as the coffee remains at the top. So that is a mud cake. The same happens now. Reverse this, tilt it 90 degrees clockwise, and the filter is the formation, and the mud cake is the formation, the consolidation of this mud against the wall. So actually, what is happening is that each of these particles here has zero effective stress because nobody's touching it. But as they begin pushing against each other, this one is being dragged by the seepage, and that drag force pushes that one, and that one pushes against the next one, and the next one picks up the drag force plus the force coming from the neighbor to the left, and it begins building up, and the effective stress keeps increasing. And what is so surprising is, imagine that you are 1,000 meters down, and this is 12 kilonewtons per cubic meter. So you are in the order, the fluid pressure here is 12 megapascals. And this goes from zero effective stress to 12 megapascals of effective stress in a very thin layer. Within a few millimeters, there is such an amazing gradient of effective stress. So to magnify this, there are different ways that we can visualize that, but imagine individuals on roller skates and with the springs pushing onto each other, and there is wind blowing. The first one only feels the wind, the next one is going to feel the push from the first one plus the wind around, and the next one successively. So the one that is finally against the wall is really going to feel the accumulation of these drugs being transmitted from the fluid onto the granular skeleton. Once again, the change in effective stress is going to be equal to the minus change in the pore pressure. So this is filter cake formation, and this is critical for TREMI operations when we are drilling big caissons, or when we use mud to drill very deep boreholes. We use the mud not only to cool the bed and to recover the cuttings, but also to stabilize the borehole. There are many other questions that remain. In both cases, whether it is in the caisson for TREMI operation or in the filter cake formation for deep wells, once that cake forms with a very high effective stress, and when we place the cement to cement the casing against the wall, or when we fill it up with concrete to form the caisson, what will happen with that mud cake? And there has been several controversial issues and stories from whether that cake actually reacts with the cement or not, or whether it becomes a preferential pathway for leakage. The last example I would like to discuss, we can talk about overpressure sediments, and we can talk about fault reactivation, but the last example is one that is of particular interest, even in the near surface, and that is if a soil is totally fractured, what happens when we put a hose inside the soil and we open the hose? It appears that it breaks the continuity of the sediment. So the medium is already fully fractured, but we can still cause discontinuities inside this mass by separating grains from each other. That is called hydraulic fracturing. And hydraulic fracturing has been argued as a mechanism for the failure of dams, and is a critical mechanism, for example, for enhanced oil recovery, for gas recovery from shale gas. So what is it? There is zero tensile strength in a sand. So it cannot be that we are overcoming the tensile strength. This is not a tensile strength failure, because there is no tensile strength in a soil without diagenesis, whether it is a clay or a sand. So what is hydraulic fracture? So let's assume that the hydraulic fracture is taking place. Let's take a snapshot. And so these are the grains. And here is the fluid pressure as it advances. So all this cavity now is filled with fluid. And this is, we just took a picture, instantaneous picture. But if we see, it's difficult to visualize in 2D because contacts in 2D really are not happening in 3D. So there is all these torture paths. But if you see water is leaking through here, and as it leaks, it's transferring that fluid pressure onto the grains by drag. And so this first grain doesn't have any effective stress. It's against water. But it's picking up the drag, and that, by equilibrium, is transferring that from the drag onto the grain, onto the next grain. So now this grain is carrying both the load that the grain against the water invasion experienced, that drag, plus the drag that is picking up itself, so it's conveying even a larger force. So these forces are very little, these ones are larger, these ones are larger, and the effective stress field that develops is actually creating an opening mode discontinuity. This is hydraulic fracture in granular materials. Please take a look at the references indicated at the end of this section.